Hello, my name is Einar Kristoffer Velén. I'm a statistician and will help Emil Stoltenberg a little bit in this course EBA 3500. And today we are going to work through homework 1. And we will start with exercise 1. And we are asked to consider the line y equal fx equal a plus bx, which passes through the points x1, y1 and x2, y2. And we also get a hint. And the hint is that we should use this connection y2 minus y1 equal fx2 minus fx1. So let's try to find expressions for fx1 and fx2. And that should be quite easy. y1 is equal, we're just putting x1 into the function and get a plus b x1. And then we can put x2 into the function, and what do we get out? We get a plus b times x2. And if we now just use the hint straightforward, we get, so let's write using the hint. y2 minus y1 is then equal, and instead of f of x2, we write a plus b x2 minus a plus b x1. And then we just open up the parentheses and we get a plus bx2 minus a minus bx1. And this gives, of course, y2 minus y1 equal, and we can see that the a cancels out, and we can factorize b outside a parenthesis, and we get b parenthesis x2 minus x1, like this. And then we suddenly, just by dividing by x2 minus x1, we see that we get an expression for b, which is equal to y2 minus y1 divided on x2 minus x1. So this was a little part of the question 1a. And let's now find, and this is the slope then. So, which is the slope of the line. Okay? Expressed as a function of the points x1, e1 and x2 comma e2 as we was told to do. So we now just have to find the intersection A. So using the expression for B, just derived above, and for example, the point x2 comma y2 in the formula y equal a plus bx, we get, okay, so we have e equal a plus bx, and instead of writing b, we write what we found, exactly e2 minus en over y2 minus y1 over x2 minus x1, and a plus this. And instead of writing y and x, we use this 1 point, x2, y2, representing y and x for this special point. And then we can get an expression for a pretty easily by just moving. We can put a here because it's nice to have it on the left side. And we understand that a is y2 minus y1 over x2 minus x1 times x2. And then we have to get all together. And we can do that by, for example, putting 1 under here and times it with x2 minus x1 and x2 minus x1 here. And then we get y2 x2 minus y2 x1 over x2 minus x1 minus, and then we get y2 times x2, which is y2 x2, and minus y1 times x2 is minus y1 x2 divided on x2 minus x1, and then we get a, and put all together on one line, we get y2 x2 minus y2 x1 minus y2 x2 plus y1 x2 divided on x2 minus x1. And then we see that y2 x2 cancel out here, and we end with an expression just changing like this. So we write a equal y1 x2 minus y2 x1 divided on x2 minus x1, which is an expression for the intersection. Expressed as a function of the point points x1, comma y1 and x2, comma y2 as we was told to do. Okay. And then we shall use these formulas just derived in an example using Python. So let's open Python, and I got Python here, as you see, and exercise 1b tells us that compute a and b when x1, y1 is 3.2 and x2, e2 is 4.8. And that is just to do straightforward. We let x1 be equal to 3. We let y1 be equal to 2. And then x2 equal to 4 and e2 equal to 8. And then we have to make expression for a and b, because that is what we are asked to find. And the general expression for a, we know that is a equal y1 times x2 minus y2 times x1, and all this should be divided on x2 minus x1. And then the expression for b, which is equal to y2 minus y1 divided on x2 minus x1. And we can then write to see what the numbers of a and b is in this special case by writing print a and print b, for example. And then we can run this code. And we see that here we have minus 16, which is print a, and b is 6. And we can also find these numbers in this variable explorer if we want to do that. So that was exercise 1. And then we will do exercise 2. And here it comes. And that's an exercise in Python. And we are asked to simulate 500 standard normal distributed numbers and make a histogram of the simulated data. But to make all this, we need some packages. So we have to import packages. I do it in the top here. So I have to import the NumPy package. And I import it as NP, so it's easier to name it. And I have to import a plot package, which we can call, which is called matplot, lib.pyplot, and we import that one as PLT. So okay, then we are good to go for exercise 2. So this was the first one. This is exercise 1B, and here we have exercise 2A, and to simulate 500 random numbers from the standard normal distribution, we do that in this way. X equal NP, and we are hunting for the function random normal, zero, because in the standard normal distribution, 0 is the expectation and the standard deviation is 1, and the last argument tells us how many x's we want, and we want 500 random x's from this distribution. And then we can print x if we want, and we will of course see 500 numbers from this standard normal distribution. So let's do it. I forgot to import these ones, so we do that first. So, and then we can do this, and we get these 500 numbers here. An array of 500 numbers contained in X. So then we can plot this histogram we are asked to do. Plot sin hist, and we are making histogram of the x's, and we don't want to have density, so density is set to false. So then we probably get the frequencies on the y-axis. Let's see what's happened. So let's run this line, and let's go to plots. Maybe like this. So here it comes. Probably case sensitive here. So then that was 2A, and then we can do 2B. So you actually see that between 0 and 1, or actually the bin width is not, it's hard to tell here, but we see the frequencies here. 2B. Then we shall make an histogram where the density is true. Okay, what does that mean? Like this, and see what happened. Now we get the densities on the y-axis. You can see it here. It's not the frequencies, it's like 0.05, 0.1, and so on. And what is the conclusion here? Let's write something. and let's write it here. The total area of the, in this case, blue, that's what I see anyway, blue histogram is now equal to 1. In the plot above, we got the counts / frequencies on the y-axis. But in this last histogram, we get the densities. Okay, and then it's 2C. And we are asked to implement the standard normal density function, but we are given the function in the text, but we have to implement it in Python. And in the exercise, they also show how to implement a function. And then we shall call this function f, and then we have to write definition of f of x. So it's this function we want to define, and it should be y equal to, I'm just using the expression in the text now, 1 divided on the square root of 2 pi, and to get pi we have to write np, to get the square root we have to write np's square root. We use the function square root from the np package, and we are going to take the square root of 2 pi, but pi is also in the package np, and therefore we have to write np, it's pi, like this. And this is going to, and we are going to times this with the exponential function, and that's also in the package np, therefore np, it's exponential function minus x in the second power divided on 2. And at last we have to return these values in some sense, return y. And to see how this function now works, we could, for example, we know we could of course write print x, but that we have done before. Then we get these 500 numbers from the random standard, from the standard normal distribution. But we could also print f of x which now will be the densities of all these different 500 x's. So let's see what happened. Let's just take this function first and see that everything goes okay. It seems like that. And okay, let's print x. This gives these 500 x's from the standard normal distribution, mostly between -3 and 3. But we have some bigger values and some lower values. And then we get the densities by this one. And let's and here we see them. Okay. Then we can do the last one. And that's D. 2D. So let's see how that works. What we are asked to do is to add the function f of x from C to the histogram you made in B. That is, make a histogram that looks like the one in figure 1. Okay, so how do we do that? First of all, I make a series here, UU equal NP, it's linspace, parenthesis -4, comma 4, and we will divide this range in 1000 parts, 10 in the power of 3. So if we want to see how this UU is, we could do that, of course. So you see it starts, this UU starts at -4. So here it is, -4, and it's divided into 1000 parts from -4 to 4, and we get these numbers. Okay, then we can plot the first I plot the histogram. Plot hist x, comma density equal true, which we actually had done before, but I do it again. And to add this density curve, then we have to use plot, sin plot, and UU, and then we call on the function f, the standard normal density function, for all these UU. And let's run this now. So we do like this. And there we got what we wanted to get. Just a remark, if I now had just, it's very different what kind of platform you use Python in. Here I use a GUI which is called Spider, and if I now just do this line, I will get this plot, and if I then go and evaluate this line, I will actually get a new plot. But if I take these together, I will get them in the same plot. So that's was exercise 1 and 2, and in the next video we will go through exercise 3 and 4. So thank you. I will also put in some extra code here, so you can try out other functions. So I do that now, but actually it's finished. So let's, for example, how to save a figure. Probably you know all this stuff from before, but this is the first homework, so it's maybe a little easy for many of you. Piltier sin save fig. Then we save a figure, and we can call it whatever we want, and I will call it my name dot apps. And now this will be saved in the working directory, this histogram here, as my name.apps, and then you can open it and see it again if you want. Okay,